today. And I also want to thank all my collaborators. This is very collaborative work, and I can't possibly list everyone here, but I saw that many of the papers were included in the abstract. So don't hesitate to consultate the authors list, to learn about everyone who was involved. And just to introduce myself, I'm Tom Beucler, and I think it was at the time, in 2021, I started the first research group specifically dedicated to the intersection of atmospheric physics and artificial intelligence. So we work on a wide variety of topics, Earth system modeling, really thinking about next-gen Earth system model and thinking about how machine learning can help build better parameterization. I'll define what these are in a couple of slides. These are little modules. They're really hard to model with traditional methods, and so machine learning really allows it to make progress towards reducing long-term climate projection uncertainty. We work on extreme weather events. We develop data-driven forecast model, think about how to post-process the new neural weather models we have available, think a lot about downscaling. And finally, I'm a professor of environmental data science, so I'm always happy to sit with scientists who have data and want to design tailored model or extract new knowledge from it. And so we really think about the two-way interaction between physical knowledge. If you're not a physicist, you can think of it as domain knowledge, and machine learning and data. And so on the one hand, I'm going to show in this talk, during the first part of this talk, that we can use this knowledge to constrain these machine learning algorithms so that they give more robust, reliable solutions. And on the other hand, I'm going to show that I think we've reached the stage where we can now, by using machine learning systematically, extract new knowledge from data, really formulate new hypotheses that may be surprising. And I think we passed the point where we just merely confirming existing theory, and there's a lot of potential that's unexplored and that hopefully will motivate a lot of research in the coming years. So just to put everyone on the same page, here I'm going to use machine learning very liberally. So also, is there a panel that on my screen? Is this better? I don't know. Now you should see the whole screen, right?
Yep, that looks fine.
Okay, perfect. So I'm going to use machine learning in this seminar very liberally to refer to any algorithm that learns a task from data without being explicitly programmed for that task. And so typically what we do is we'll target uncertain process. This is a movie from the North American monsoon, and it demonstrates how convection, which is any fluid motion driven by density differences, can transport dust. Here it's very visible. It also transports other important traces for the atmosphere, temperature, water species. And these are the type of processes that are really hard to model using traditional pen and paper techniques or semi-empirical parameterization, but we have data for these processes now. We have high fidelity modeling data, we have observational data, and so we really target processes for which there may not be a clear theory yet. And in a supervised setting, we'll typically map an input vector, x, or more generally, it can be a function as well in the operator learning framework. And for the input vector, we'll try to map from quantities we know and understand better. This is an example in a traditional, so relatively coarse things, think 100 kilometer in horizontal grid scale, general circulation model. What we understand quite well is at these large scales how temperature and the concentration of water vapor are distributed with height. And machine learning allows us to train a mapping that goes from the left-hand side that we know better to the right-hand side that we may not know how to model really well, but we have data for. And in standard supervised setup, Algorithms such as neural network can approximate this mapping by minimizing a loss or cost function. A very standard loss function will try to minimize the difference between what the model predict and what you get from the data, and will often, especially for large data, will use variants of stochastic gradient descent. And this works really well, and if that works really well, you may ask, okay, do we still have a role for physical knowledge, and how can we use it? And in the first part of this talk, I want to present some of our work on physics-guided machine learning, and I want to make the point that we can go way past the more traditional physically informed neural network paradigm, where we use exact equations and a physical knowledge to constrain the loss function. I'll show that we can think of all kind of knowledge to restrict the solutions that our algorithm provide to plausible solutions. We can improve physical consistency. I'll also show how we can improve generalizability across regimes, in some cases extrapolation, and I'll also discuss about reduced error in this seminar's first part. I put a little star here because unfortunately there's no free lunch. I mean, I don't know if this seminar provides free lunch, but in general, there are compromises, there are trade-offs, but sometimes we get lucky. I'll show that in an instant with the first example, and the first example I'm gonna present is physically constrained post-processing, and don't worry, I'll go over the definition of each of these terms. So I want to start in a really simple, low-dimensional setting. It was my first collaboration with Meteor Swiss, and at the time, it was an excellent PhD student who's now a postdoc, Francesco Zanetta, and he came with this problem that if we post-process surface weather naively with machine learning, it violates physical laws. So just to give a sense of what post-processing is, this is a really nice visualization from Meteor Swiss about the transition from the previous mesh, from the model they had before Cosmo, to the new mesh of the German model they now use for weather prediction called ICON. But regardless of the mesh, these models that we run, the dynamical models, so that integrates the equations of motions and time, are on a mesh that cannot possibly cover every single village we want to make forecasts for. And Switzerland is a particularly good example because maybe the village will be trapped between two mountains and wind can only blow in a very specific direction. And the model on this mesh, it's not that coarse, but it's too coarse to resolve such really local phenomena where you may be protected from a specific type of storm. But what we do have is we have an observational record of the weather at that location over the past now half a century, pretty much, even more, but we can use at least a high quality part of the observational record to train a model that goes from the output of that dynamical forecast to what you'll read on your phone. So what you read on your phone is never the direct output, but it's the post-processed output where a model has mapped these coarser predictions to observations at a specific location, and that's how you can get such accurate weather forecasts. The advantage of machine learning in that case is that instead of training a linear model per day, per station, etc., you can just have a single, or at least a much lower number of larger data-driven models, for instance, neural networks that can take the station ID, the day of the year, etc., and post-process all, in that case, it's more than 200 stations at once. And so the prediction problem can be written as something that goes from the output of the dynamical forecast model to 5 surface variables we care about using observational data as a reference. And so in that case, we'll post-process from top to bottom absolute temperature, the dew point temperature, so that's the temperature you need to cool the air to at constant pressure to reach a relative humidity of 100%, which generally forms a cloud. So that's smaller than temperature. Then we're trying to predict surface pressure, relative humidity, and the water vapor mixing ratio. And in the atmosphere, we know that these variables are not independent. We have two physical laws that allows us to relate these 5 variables together and introduce a multivariate dependency. And in that case, it's the ideal gas law, which can be for an ideal mixture of dry air and water vapor, which can be rewritten as a function linking pressure, this variable, to the mixing ratio, this variable, via the partial pressure of water vapor, and that partial pressure of water vapor can be related to the dew point temperature by integrating what we call the Clausius-Clapeyron equation, which governs thermodynamic quantities when the phase of water change from vapor to liquid and ice, basically when you form a cloud. And no need for those of you who don't do atmospheric physics, all you can remember is that in that case, it's a very nice case where we have 2 equations relating these 5 variables together. So we can write the last 2 variables as a function of the first 3 ones. And if we train an unconstrained neural network, typically it will take shortcuts. And if we scatter the residual of these 2 equations as a function of relative humidity, we'll get residual of order 10%, for relative humidity, which is typically between 0 and 100%. So this is large. On the right, I'll track the normalized mean absolute error. No need to care too much about the numbers here. All you need to know is that up is bad, down is good. We're trying to lower this. This is the error of the unconstrained model. And here, I'm placing myself in a low sample case to show the benefits of physics-constrained machine learning. We can discuss this more at the end of the seminar if some of you were interested. But here, I'm just using 1% of the training set to really highlight the trade-offs. So we know these 2 physical relationships. In that case, they're exact. So why not use them? And the simplest way of using them, which is very close to what physically informed neural networks do, is just to add them to the loss function. So we're optimizing how close our predictions are to the observations. Why not just also add a regularization term? In that you can throw in whatever norm of the residual of the equation. Typically, it's better if you take a norm that has the same units or the same mathematical properties as the loss function used for performance optimization on the left-hand side. And then you have a regularization coefficient here, and the more I crank it up, the more I force the neural network to follow these 2 conservation laws. Now, the problem, and you can already see it here, is if I have infinite data, this works really well. Because then I just have enough data to optimize the entire neural networks. I tend to not have a trade-off between these 2 terms. But if I don't have too much data, I'm constantly going to be wondering what value to assign to lambda. And in that case, I'm going to get a slightly worse performance. So I've reduced the residuals, although they're not 0, because the stochastic optimization rarely will almost never give me a 0 loss. And then I've degraded performance. And so to avoid that game, what we can do is we can completely rethink the architecture of the neural network or the machine learning frameworks. There's not just one way of doing this to exactly enforce these 2 equations to within machine precision. So in that case, what you would do is you would take, for example, 3 variables. You would predict the 2 remaining variables as residuals using the 2 exact equations you know. Then you concatenate the entire thing. And the trick here is to keep everything inside the machine learning framework. So for example, you can write this in PyTorch, TensorFlow, JAG, pick your favorite machine learning language, and then you optimize the entire thing. So you write this as a physically constrained layer, but inside your neural network. And so by doing that, the final weights and biases of your neural network here will know about these 2 analytic constraints. And by doing that, sorry, we have automatic blind closing and opening schedule that's broken. So my image, the brightness will change, but hopefully the screen will stay the same. By doing that, we can get, in that case, better performance and enforce the constraint to within machine precision. So this is one of the rare cases of free lunch. And I interpret this as the dimensionality of the constraints here is very close to the dimensionality, the effective dimensionality of the mapping. And so here, by just giving two constraints, you already give a lot of the answer, and you're searching a solution in a much smaller space. These methods can be generalized to nonlinear constraints, to much broader physical problems, and that's why we were able to publish it in physical review letters and make it useful for all fields of physics. But the takeaway here is that as long as you have exact domain knowledge that you can write in the form of analytic equations, there are frameworks, many different ways of enforcing it to within machine precision. But now many of you are thinking this is a luxurious case. Even in the atmospheres, there's not that many equations that we know exactly, definitions, state equations. But if you think of budgets, often the sinks and the sources are intractable. So even when you go to equations you think you know, sometimes just getting all the terms in the neural network or the machine learning framework you're using is hard. So in many cases, you have knowledge that's slightly different. But it can be robust knowledge, even if you can't write it in the form of equation. And that's a second example I want to present today, a case where you can use knowledge of atmospheric physics to help neural networks generalize across climates. And here I'm going to go from a weather forecasting example to a climate modeling example. So we're going to look at the problem of machine learning-based parameterization. And so I'll give you a bit of context of what machine learning parameterization is and why do we care. So as atmospheric scientists, we're never happy with the quality of our Earth system models. We always want them to get better. They can do some things very well, projecting global mean surface temperatures, but sometimes we want much more local predictions. And they have a wide variety of biases. One of them is that because of computational cost, it's really hard at the global scale to simultaneously simulate clouds. I think I showed you a movie of convection that not that large, convective events are not that wide in scale. You know, it can be a couple of kilometers, but you saw how important they were for vertical transport. So they order one for vertical transport in the atmosphere, yet simultaneously simulating the winds at the planetary scale and these convective events is way too costly. It's still too costly for routine ensemble climate projections, but different modeling centers have been able to run shorter versions of these simulation that had simultaneously resolve planetary scale winds and deep convection. So think of models that can go down to a grid spacing of 3 to 5 kilometers in the horizontal. You resolve deep convective storm while also simulating the planetary scale simulation. These simulations are way too costly to be run for hundreds of years, but you can run them for 1 or 2 years, and they produce a lot of data, and that data we can use for machine learning via coarse graining. So if we take that data, coarse graining the time and space, what we can learn is from the perspective of coarse models that are cheap enough to be run for ensemble climate projections, what is the aggregate effect of these 5-kilometer storm cloud turbulent processes? So what we can do is we can use this coarse grain yet high fidelity data as training data. And then neural networks can mimic, the technical term is emulate, the effect of these storms and clouds on the planetary scale climate, even in realistic geography configurations. So these are results from, well, the first PhD student I was able to co-supervise from start to finish at UC Irvine. And what he showed, that was his thesis first chapter, is that neural network, even in realistic geography configurations, can do a pretty good job at emulating the resulting effect of these subgrid scale tendencies. So at the top is what you're trying to emulate. So the effect of storms and clouds. Here, sorry, one second. Here, we're looking at data from what we called a super parameterized climate model, where in each grid cell, the effect in each grid cell are embedded 2 or 3-dimensional storm resolving models, and at the bottom is the neural network. On the left is how much water vapor is redistributed in height and in the middle of the atmosphere, roughly 600 hectopascal. And on the right is the precipitation rate. And you can see that to first order, the neural network is a bit too smooth here. We trained it using a mean squared error, but it does a pretty good job. But the problem is that if you take these same neural networks and you expose them to climate regimes they've never been trained on, and here we design experiments on purpose to break them. So I'm a physicist, I like to break models, that's part of my job. So these images are just to illustrate the idea. That's not actually how our simulations look. The idea is you train and validate machine learning models like the neural networks I showed you just earlier on cold simulation, and then you warm the surface by 8 Kelvin, which we hope will not happen in the near future, and then you test them on much warmer simulations. And if you do that, this is a different view of what the neural network has to learn. On the left is the amount of water vapor redistributed in height as a function of height. Here is the ground, here is space. On the left is moistening, on the right is heating. The neural networks make mistakes that are order 10. And that's, I would say, really helpful, because if you're going for errors of 2 or 3%, it's really hard to know what works and what doesn't, especially if you vary machine learning frameworks, optimization, you do a bit of cross-validation. But you have an error by a factor 10, you really can see what works and what doesn't. So if we think of it from a statistical perspective, and we think, and we look at the mapping, so here I'm showing the marginal distributions of the different inputs and the marginal distribution of the outputs. What we see, if the blue curve represents the cold climate and the red curve represents the warm climate, is that if I just take the raw data and I throw it into my neural network, it fails. And what that suggests is that the mapping going from left to right is not the same in the cold reference climate and in the warmer climate. In other words, the neural network is not climate invariant if the mapping is framed directly using the raw data. But now we have knowledge of how that data change, how these data change with climate through what a subfield we called moist atmospheric thermodynamics. For example, we know here why the atmosphere is much more humid in a warm climate than in a cold climate. So this is another way of visualizing this extrapolation problem. But we know that the reason it goes up so much is that because the amount of water vapor a given atmospheric mass can hold increases near exponentially with temperature. So we know why we're going from that blue curve to that red curve. And we can use this equation, the Clausius-Clapeyron equation, to rescale the specific humidity variable in what we call relative humidity. And now we go from a problem that's extrapolation to a variable that's mostly between 0 and 100%, and the neural network can handle it. These distributions don't necessarily need to be on top of each other, but we go from an out-of-distribution problem to something that's out of sample, but close to identically distributed. And just with this transformation, the generalization improves dramatically. Now we can play this game with all the other inputs of the neural network. And once all of these input vectors transformed, we get a much better generalization skill. And what that suggests is that now we went from a mapping that's different, if we look at different climates, to a mapping that's much more invariant across climate. It's not perfect invariance. We can talk about it afterwards, but at least it's approximate invariance, and it's approximate enough that now the neural network generalizes well. even in more complex Earth-like configuration. Here I'm showing a map of error. This is the coefficient of determination, not to be confused with the coefficient of Pearson correlation coefficient. So it's 1 for perfect prediction, 0 if the error is as large as 1 standard deviation, -1 if the error is as large as 2 standard deviation, and can go all the way to -infinity. And once we transform the data, we go from a situation where the neural network really struggles in the warm tropic, because that's where it's exposed to sample it's never seen before, to something that's acceptable globally. And so we were able to transform the data to go from an extrapolation to a problem that's much closer to interpolation and facilitate generalization. So here we've used physical knowledge that we didn't necessarily that we weren't necessarily able to write in the form of a closed equation, and we still it still provided a lot of benefits. And that kind of ends the physics-guided machine learning part, and I'm going to now go to the data-driven discovery part. Now you can ask, okay, why does it work better? Even in this case, where we generalize better. And the way we analyzed why it performed better is using SHAP. Maybe some of you are already using it. It's one of the many explainable artificial intelligence methods that can be applied post hoc. This is a high-dimensional mapping, so the way we analyze it is we form nonlinear response matrices, and it tells you how an output at a given level reacts to an input at another level. And so here, if I take a point here, for example, I can see how the subgrid heating responds to changes in relative humidity. Blue means there's a positive correlation. Red means there's a positive correlation. Blue means there's a negative correlation. And if I compare this new climate invariant mapping to what I had with the raw data, what you can see to first order is that I have a bunch of red and blue on the right, but it's much closer to the diagonal on the left. So what that suggests is that the mapping that I learn is much more local in the vertical. So if I change an input at a given level, I get a response of the output that's mostly at the same vertical level. And this is really interesting. Well, from an atmospheric science perspective, I'll summarize it in 10 seconds. It just means that we gave the neural network enough information to know about when the cloud is formed and how the boundary layer communicates with the troposphere. And that's why it's much easier to learn. The space of solutions you have to look through is much smaller, and you're much more likely to learn something that's generalizable. And so during the second part of the talk, I want to talk much more broadly about all the methods we may be able to use to systematically extract knowledge from data using neural networks. And so I want to introduce a pretty general concept that we call Pareto-optimal model hierarchies that can be applied to different fields with different algorithms, and explain in concrete cases how we can use it to systematically distill knowledge, potentially new knowledge, sometimes knowledge we already know, from data using machine learning algorithms. And if I have time, I'll talk a little bit about challenges and why there's still a lot of work we need to do in that field. And the motivation for this work is that the added value of machine learning is measurable. Many of you have probably witnessed it in your respective fields. We can see it using performance metrics typically, and we can see large improvements in different types of performance metrics in different fields. Here, and sorry, give me 1 second. Sorry, I'm still a bit sick and congested. In my field, at least I work a lot on weather forecasting. We've witnessed a really big revolution in what we call medium-range weather forecasting in the past couple of years. So here we're showing the ability of machine learning models to predict what we call 500 hectopascal geopotential height. This is a diagram that's really nicely done by Stephen Hoyer and Stephen Ras from Google that shows you that as we progress throughout the years, the deterministic skill to forecast that variable has improved to the point where we beat the state-of-the-art dynamical forecast that'll run of thousands of computer cores. This is IFS from the European Center for Medium-Range Weather Forecasting. I guess you're really close to Reading, so most of you probably know where this is. And recently, Pangu from Huawei and GraphCast from Google, and then the neural GCM from Google have really been able to outperform this model in a deterministic sense. And so we know there's something to learn here. It's probably related to some improvement in predictability, but it's really hard to explain. And this complexity reminded me a little bit of what happened with climate model or system models, where over the years, as we added more and more processes in the Earth system that we wanted to represent, we've evolved from really, really simple climate models that were just balancing two terms in an energy equation to much more complex beasts. And we face the same problem where we could make better prediction, but we couldn't necessarily explain what was happening. And one of the tools that emerged in the 90s, 2000s, and now it's used systematically is called climate model hierarchy, where you can organize model based on their complexity to better understand the added value of that complexity and be able to explain it in human terms. And that's exactly what I'm going to use, but this time with machine learning model. So the idea of Pareto-optimal hierarchy is quite simple. It's to not throw out the models you train, keep all of them, and place them in the simplest case. This can be generalized to ND, but in the simplest case, in a two-dimensional plane, where on the x-axis, I'm representing model complexity, and on the y-axis, model error. So the message is keep all of your model, scatter all of them here on this plot. And here I've trained a lot of different models. And now you can ask which ones are the best models. And because you have more than one performance metrics, and you can add any other undesirable properties you're interested in here, so physical inconsistency, etc., there's not a single optimal solution. Instead, what you have is a set of optimal solutions. You know that you want to minimize these two, so you know you want to go to the bottom left. And so you suspect the solutions are probably in that region. And in multi-objective optimization, a really useful concept is called the Pareto front. And it was defined, it can be rigorously defined as the set of models so that if you switch to a different model, you have to sacrifice at least one of the evaluation metrics. So in practice, here you want to go to the bottom left. All you have to do is to draw a staircase from the top left to the bottom right. So if I draw a staircase, the set of optimal models is here. And what machine learning is really good at, especially deep learning, is at exploring large multi-dimensional spaces, sometimes using multimodal data. And it's really quick at finding a complex solution that works well. So you use a lot of data and you find a better solution here that dramatically improves performance using deep learning. But then what I argue is that we shouldn't stop there, especially if our goal is knowledge discovery. You can always stop there and say, you've built a great model that has low error. But it's really hard at this point to explain what happened because you're in a high complexity regime. And so we can think about what kind of knowledge can we distill? What kind of knowledge can we learn? And I find that writing the model with a really simple equation can help us understand that there's not that many reasons this machine learning model was able to improve performance. So here I'm going to put myself in the geoscientific context. And what we have is an output that's a function with the model of physical fields in space and time. So here I'm referring to the fields with X. These are the features of a model. They're discretized in space and they're discretized in time in a standard machine learning framework. And so in the end, we can only act on these terms to improve the outcome Y. So maybe the machine learning improved M. So it found a better function. You started from a line, but now it was able to learn a nonlinear function. You started from a deterministic function, but it was able to learn a stochastic mapping and added value via uncertainty quantification. So you can improve the functional representation of your model. Maybe it was able to assimilate features that you've never seen before. And that I would refer to as feature assimilation. Maybe it was able to connect points in space. So for example, convolutional neural networks can, well, to give a climate example, connects points in the Earth that are very far apart and that you didn't think affected one another. Or we can use sequence processing algorithm to learn new temporal connectivity. And so once you're able to identify what the machine learning model was able to do that it wasn't able to do before, you can then try to distill this new knowledge. And the act of distillation is to bring back this model to a lower complexity point without compromising performance too much. And that's what we call distillation. And I'm going to give you an example right away. An equation discovery, data-driven equation discovery is an example of distillation, where you're able to bring this back to an interpretable simplicity setup without compromising performance too much, and then systematically distill knowledge from data. So I'm going to give, I should keep an eye on the time. I have 10 minutes. I'm going to give one example, which is cloud cover parameterization, in which we're able to discover a new equation from data. So it's similar to the parameterization setup I showed before. What it does is that it can map so what we're trying to do is to improve the representation of clouds, because clouds, especially cloud cover, affect radiative biases in the atmosphere, and they really increase the uncertainty in the long-term climate projection. They're one of the terms that makes it hardest to fit our climate models to observations. And so what we're going to do is we're going to take storm resolving model data, like I showed you earlier. At this really, really high resolution, you can say if the amount of cloud condensate is above a certain level, there's a cloud. And so you pick a threshold, and then you have high resolution 0 and 1. Then you can bring it back to the resolution of coarse climate models by coarse graining this field. So now you have continuous numbers, which represent cloud fractions. So you can say I have 20% of clouds of cloud cover in my grid cell. And once you've done that, you get a coarse resolution but high fidelity cloud cover that you can learn with machine learning. And to make the point that this is a non-trivial problem, here's another North American monsoon movie. You can guess that I really like Storm Chase's movie. And I ruined this movie by drawing a voxel here. And here what you can see is that it's a non-trivial problem because very different cloud configurations can lead to similar cloud cover. And I'll come back to it later. You can have this almost filled with thin clouds, or have a really big clouds and have very similar cloud cover. So I'm going to do exactly what I described. First, I'm going to train a lot of baseline models, linear models, polynomial models. Here's the baseline we're trying to beat. It's the parameterization that was in the model that we're trying to replace with machine learning. It's bad, not because people made mistake, but because at the time climate models only didn't predict liquid and ice clouds very well, so it only depends on one variable, relative humidity. Here's a really good one from David Randall and Wang that only uses 4 parameters. And I'm using sequential feature selection to populate this first baseline plane. And once we have these baseline models, what we did, and by we, I mean it's a PhD student from the German Aerospace Center who trained neural network to emulate cloud cover. He was able to learn high resolution, the cloud cover we got from the high resolution simulation really well using neural networks. So before we couldn't really go below root mean squared error of 15%, and now we can go below down to 7%. So we were really able to find a step improvement in performance using deep learning. And now the last step is to distill this knowledge. So now we have neural network, but they have 10,000 if not 100,000 trainable parameters. Cloud cover parameterizations are typically simple. Ideally, we'd like to condense that into something that's much lower dimensional, but still has the benefits that we found in machine learning. And you remember one of the main advantages of machine learning is feature assimilation. It can handle correlated features that are non-linearly related to the output. So what we did here is we performed nonlinear feature selection using neural networks. We found the 10 features that led to the best performance in a nonlinear way. And then we threw them, I think we even went down to, in that case, we even go down to 5 features. And once you have 5 features, you can use symbolic regression algorithms if you want to distill these neural networks into equations that have similar performance. In that case, we use PySR. We also tried GP-GOMIA or other symbolic regression algorithm that are all many of them are publicly available. They compare, they benchmark. And then what we do is we use a set of physical constraints to only keep the equations that follow these physical constraints, the asymptotic constraint on derivatives, etc. And we can distill the best neural networks, or at least we can distill this problem into a 3-term equation that we can then interpret. And in the end, we found, and that's the fun part, when you've done this distillation, you can wonder, okay, what did we learn? What did we already know? And what is new? How did we get this jump in performance? And so here we get 3 terms. The first one is a Taylor expansion about the mean training set state in the 2 most important thermodynamic variables that's expected. Now, the first term that wasn't necessarily expected is this inversion term, where the neural network was able to identify the relative humidity gradient as a feature. So that's the example of feature assimilation. It's also nonlinear, that was able to place the low stratocumulus depths at the right place. And that's really important because these are responsible for a lot of our uncertainty in shortwave radiative budget. And then another surprise is that the model found a monotonically increasing function of liquid and ice. We expect that, more cloud cover. But it put different coefficients in front of liquid and ice. And then that's where maybe there's a surprise. And I think that's where we reach a stage where maybe we can ask ourselves, why did we learn that we didn't already know? And in that case, we asked ourselves, okay, why did we get different coefficients for liquid and ice? And then you can think more about the problem. All you have access to is the mean liquid and the mean ice in your voxel. And because they're not distributed in the same manner, the slope of subgrid ice is much steeper than subgrid liquid. Then you can think, okay, if I have a given amount of ice, it means that I have a lot more clouds that have lower value in my grid cell. And then we proved analytically a posteriori that this made sense and that coefficient should be larger. But it's really an example where we were able, by performing knowledge distillation, to bring back what we learned to a place where we potentially were able to formulate new hypotheses about processes that we didn't necessarily know about. And this is also an example of transparent machine learning. Once you have an equation like that, well, you're likely to be closer to first principle. Maybe it's not exactly first principle, but you're likely to be one step closer to it. But also, it's grid independent. You can share it with, you can use it in different models. It's much easier to transfer. It's easier to communicate. It's easier to constrain. And importantly, for climate modeling, it's easier to calibrate. So once we couple that parameterization back to the entire climate model, and these are recent results, the credit mostly go to Arthur Brunner and Julien Savre in Veronica Ehring's group. I work with them, and what they showed is that by going with this new analytic equation, they were able to calibrate the top of the atmosphere radiation budget much more easily. So they can go down, the bias goes down by 2 watts per meter square if compared to observations, just by replacing the cloud cover parameterization with this new data driven form. And unlike neural networks, that have 100,000 parameters. That's really hard to calibrate once you couple it back. This one only has 10 parameters, but it still gets you most of the improvement of neural networks. So I hope that what I showed is that to answer a question I often get, so I'm always asked, okay, have we learned anything new using machine learning? Well, it's hard to answer yes, because new knowledge needs to be confirmed by the scientific community. It usually has to go through more experiment, more targeted observation, at least as potential. If we recycle all of a model and we organize them systematically, and that's described in the paper I attached, there is potential to at least formulate new hypotheses that may be surprising. And then I had the last problem about the stochastic or high-dimensional case where we're really trying to explore, okay, how do you distill? So if you go in that paper, I also give examples on spatial connectivity, temporal connectivity, how do you understand the benefits of memory versus zooming it in space? And then I wanted to talk about challenges linked to stochasticity and dimensionality reduction in cases where the mapping may not be trivial, but I think I want to be respectful of time. So it's already 50. Do you want the last example, or should we switch to the question session? And I'm very happy to do either, because I know this is a lot of materials. So are there opinions?
Of the people in the room, who has to go 5 minutes? Okay. I think we've got time. Yeah.
Okay, so I'll give a 5 minutes overview of a much more challenging problem in which it's not a simple equation. The process is not order one. What that often happens in complex system. And then what can we do? And these are really the kind of challenges we think about these days in the lab. The cloud cover is a nice example because the equation is local in time, in space. You know, it's the relationship is order one. But for example, if you're thinking of radiative feedbacks on tropical cyclogenesis, and I'll define that in a second, this is not always an order one process. It's a process that's new, that's newly considered in the sense that in the traditional paradigm, tropical cyclones, especially ones they form, are mostly influenced by the environmental shear, which typically acts against tropical cyclone intensification by disrupting them, while they're powered by the amount of energy they can extract from the ocean and the environment more generally. But some simulations, some results that I'm showing here are really provocative. This is a simulation, but of a real tropical cyclone case. On the right-hand side, these are simulations by James Rupert. On the right-hand side, the cloud radiative feedback was made horizontally uniform. And if you do that, you prevent the tropical cyclone from intensifying nearly as much. And what that suggests is that radiation or cloud radiative feedbacks can have an order one effect, especially in the early phases of tropical cyclone intensity changes. And these correspond to some of the most open questions in tropical meteorology. These early stages where convection organizes in a rotating frame, or where an existing disturbance may or may not intensify during tropical cyclones are really hard. And traditional theories can allow you to understand what's happening to some extent. And so for those of you who are atmospheric scientists in the room, you can combine the momentum and the heat budget and make a lot of assumptions. So you assume the cyclones is axisymmetric. You assume that the changes are slow, or and then you can write what we call the Sawyer-Eliason equation, which tell you why the secondary circulation here, so the tropical cyclone intensifies this way, the primary circulation is here, and then the secondary circulation is the one that's able to intensify the tropical cyclones by bringing radial momentum inwards. You can show how the heating that results from clouds may intensify the circulation, but you made a lot of assumptions. And that's why you can ask, maybe I can use machine learning to make less stringent assumption and directly understand the effect of radiative feedback on tropical cyclones. And so what you can do is you can directly target the tropical cyclone intensification rates, Here I'm seeing that there's only 5 minutes left in the Teams meeting, so I don't know if there's a way to re-invite me once it shuts down, but hopefully there is.
We think it should be fine. It shouldn't end automatically.
Okay. So what we can do is we can design interpretable machine learning frameworks to directly learn how the different types of radiative feedback affect tropical cyclone intensification rate. And here, what we're trying to do, the problem is it's really a high-dimensional problem. We're looking at 4D fields, 2 intensification rates. What we're trying to do is extract patterns we can interpret. We know we may not be able to write simple equation, but we want to. So that's our dream. We want to still be able to write that the tropical cyclone intensification is equal to a long wave plus a short wave contribution. But we know these contributions may not be order 1. So we need to design an appropriate machine learning framework. And so what we ended up converging on is a variational encoder-decoder because we need to reduce the dimensionality of these fields. And we made it interpretable enough that you can write this as a simple equation where you're saying how much the radiation projects on a pattern that I'm going to learn from data will tell me whether the tropical cyclone intensifies or not. So to put it in picture, you take the long wave field, you look at its anomaly, and then you learn a 3-dimensional pattern from data. And if it projects positively onto it, you get a higher intensification rate. And if it projects negatively onto it, you get a low intensification rate. And if it doesn't project onto it, so if the projection is 0, then the process does not have an order 1 effect. So this is pretty powerful because I'm able to still machine learn a relationship even though the process is not always order 1 by framing it in a probabilistic way. And so here I can still write a really simple equation, whereas before I had to make all kinds of assumptions. Now I can just write, okay, the intensification is a long wave and a short wave contribution, where these random variables are sampled from a normal distribution whose mean is a simple projection. And then once I have that, I can look at the pattern and try to make new hypotheses. So it tells you where you should put clouds, where you should put radiation if you want your tropical cyclone to intensify. And we get this high cloud effect that we expect. But for example, here we can see a shallow convective effect, which was suggested in the literature, but not necessarily systematically shown before. And on top of that, we get signatures that are very asymmetric. And that's different from what we get from the traditional theory. And what it highlights when you dig deeper into it is that where you heat the cyclones matters a lot because you're trying to protect the cyclone from the shear. So if you heat it where the shear attacks it the most, then it's more likely to keep intensifying. But what you can see is that here, these data-driven frameworks were able to help us make assumptions or new hypotheses that then we can explore using all kinds of different techniques, where traditional frameworks may have been limiting. And then we can create new theories, new ways to think about it, but we can also use this algorithm to make probabilistic prediction. And so that's the end of my talk. And what I hope I convinced you of, or at least planted the seeds for, is that when we think of physics-guided machine learning, we ought to be much more creative than the standard physically informed neural network framework. There's a lot of literature on that framework because it's easy from the mathematical side or the fundamental physics side to think of equations and how to constrain the machine learning framework with. But I think many of you in the room have knowledge that is not necessarily, that cannot necessarily be written in the form of equations. And in that case, you can think of many creative ways to use that knowledge to make the prediction of your machine learning algorithms more plausible. And then for the data-driven discovery part, there's new understanding I think we can derive from large data sets and from well-designed machine learning models. And in that case, the message is this: you can look at this problem with all kinds of algorithms as long as you keep track of their performance and you really focus on the added value that you get from each complexity units. And I think this has a lot of potential because these hierarchies that I showed you, they're all trained on the same data set. So you can attack realistic end-to-end problems with a hierarchy of models and extract knowledge without having to make compromises, without having to necessarily place yourself in an idealized or simplified setting. And I think we're only scratching the surfaces. And as long as you leave room for surprises in how you build your data-driven frameworks, there's a lot of potential to formulate hypotheses that we wouldn't have been able to think about before. So thank you, and I'm happy to take questions.
Thank you, Tom. That was a very comprehensive talk. Do we have any questions? Phil.
I have a question for your talk. Can you hear me?
Yes.
Right. I have a question on the data or data discovered physics topic that you discussed.
Yeah.
So you described a method where you take your data and you fit a deep neural network, and from that you derive the physical equations. There are other methods which you can go directly from the data to a reduced set of equations without going via this deep neural network. Could you just say something a little bit about what the added value of this extra step is?
No, it's a really good question, and indeed, I mean, and maybe that I didn't explain this properly. You can ask, why couldn't I just directly go down here, right? Why can't I just throw the original data in a symbolic regression algorithm and constrain it, formulate it in a way where I can directly get to that bottom left corner? And the answer is the curse of dimensionality. Many symbolic regression algorithms don't react well to a high number of features. And here we had hundreds of possible polynomial features, derivatives, etc. And most symbolic regression algorithms pretty much, they don't necessarily break, but they don't give you great results if you throw in more than 5, 6, 7 features. And so if you try to brute force this problem and just throw it into a symbolic regression algorithm, you end up here. You end up with a polynomial solution, and you don't get a performance that's rivaling some of the neural networks. And so in that case, neural networks help you for nonlinear feature selection. But there's other papers, there's one that I really like by Diane Hefner that's called Rogue Wave Equation Discovery, where you don't just use it for feature selection, you can also use it to learn the separability, so the additive or multiplicative separability. You can also use it to learn the features for generalizability that allow you to generalize best between different regimes. And you can also use it, that's a problem I showed right after, for dimensionality reduction. So to learn the optimal way of reducing the dimensionality of your problem. So I guess to summarize my answer is that except if you're in an extremely low dimensional problem, and usually these problems are already solved, I mean, there's a couple of them that aren't, but the problems we're really struggling with are usually high dimensional, nonlinear. Symbolic regression don't scale well, so you can use neural network to restrict the function, the feature space, until it's a good candidate for symbolic regression. And in my mind, that's a bit what separates just symbolic regression from equation discovery, and I'm happy to talk more about it, because I don't think symbolic regression and physical law learning are synonymous. I think there's more steps to go to equation discovery than there is to just do simple symbolic regression. Sorry, I don't know if that answered your question or...
Yeah, that's a great answer. Thank you.
Okay.
Jason?
Thanks for a fantastic talk. I really enjoyed it. So you use SHAP values to kind of find the features that are most important. Do you use other feature importance techniques, or do you think it's not necessary because SHAP values have some explainable features that are absent of many of the others?
I couldn't hear the question very well. Is there a way to do you have a microphone or something? I think it's just I got some of the I heard SHAP.
Yeah, do you want to just come up here?
I can just I'll just go up.
Yeah. If you stand here, you can see you. Okay.
Hello.
Hi. Yeah, thanks for a wonderful talk. I really enjoyed it. I was wondering, you use SHAP values to find feature importance in some of the work. So sometimes I find that the different feature importance methods give different answers.
Right.
Do you think SHAP is just because of its axiomatic features. Do you think it's just the best one to use, or?
I like it because it's mathematically convenient because the importances sum up to the anomaly in the output. So then it's a nice mathematical object to work with. I don't think it's perfect, and different versions of SHAP make different assumptions. Yeah, I mean, I think that's the unfortunate part, right? Like each feature importance method makes assumptions, and these assumptions come with limitations. I just find SHAP really easy to work with and to be quite reliable. And what's nice with SHAP is that there's a kernel version that can be used across models where you don't have to commit to a certain model family. But yeah, I mean, I'm not saying the other feature importance methods are not necessarily good. There's a lot of papers on the limits of post hoc XAI, and that's why in the group we're going more towards interpretable machine learning. And at the end of the day, if you really want to understand the information content of different set of features, ablation experiments are the way to go, right? And that's what we do when we do these hierarchies, right? It's better to just completely deny a feature to a model then rely on the model to understand the feature importance because it may have made its own choices and maybe this is not a unique solution. So if you have the compute, ablation experiments will always tell you more. If you don't and you're stuck with one model, then I find SHAP to be nice. I don't know if that answers the question.
That's a great answer. Thank you very much.
Okay, do we have any other questions? So I had a quick question about the climate invariant machine learning.
Yeah.
So in the case of humidity, relative humidity and specific humidity, it makes sense as why that works, why the distribution doesn't shift when you use relative humidity. For other variables where we lack that kind of intuition, is there a systematic way of finding the invariant variables?
I think that's a great, I think that's a great question. In that case, specific humidity was the easy one, even though it was the most effective one. And then it took me a good year and a half, I think, to find a good. In that for specific paper, I was really I was really trying to only consider physically informed transformation. And for temperature, we found that the moist static energy conserving plume buoyancy formulation that's used a lot in, we had collaborators with at UCLA, so from David Neely and Fayez Ahmed's group, worked really well to align the temperature distributions without losing information. And for the surface enthalpy fluxes, we use the bulk aerodynamic formula. So in that case, we're able to find transformation for each feature, but it took me a long time, and I was a postdoc and I had a lot of time. It was COVID. I would say this is not necessarily something you can do every time. So in the more general case, I think you can set up your cross-validation in a way where you can optimize for the transformation, right? So nothing prevents you from, for example, separating your neural network. I mean, you can do it with many other machine learning algorithms. I just find that neural networks are nice because they're very flexible. So you could very much learn transformations for each feature so as to optimize the ability to generalize from one regime to another. In that case, you have to set up the cross-validation in a very specific way, where different regimes describe hard generalization exercises, and you keep track of the generalization performance. But I think you could, with a bit of creativity, maybe two-step learning, maybe cross-validation, you could systematically learn that transformation. You could even force it to be symbolic by designing your layers in a specific way. So I think there's ways to do that. I don't think it's trivial. I think it's a current research topic, and we're doing a bit of it. Other groups are trying a little bit too. I think there's many ways of doing that, but the difference compared to physically informed methods is that you need generalization data. If you want to learn it systematically from data, you need to have enough samples from the regime you want to generalize to. Whereas in physics, you don't, if you assume that your physical law is valid across these regimes. Does that answer the question?
Yes, it does. Thank you.
Okay, cool.
Okay, if we don't have any more questions, then let's thank Tom once more.
Yeah, thank you so much for inviting me. I wish I could have come in person. I find it's hard to see the audience and interact, but I hope it was clear enough. And I'm available by email, or I guess by Teams. If anyone has questions, don't ever hesitate to ask. And I think I linked all the papers, but yeah, if a question comes up, I'm happy to take it at some later point.
Okay, thank you.
Thank you so much. Have a good one.
Bye.